Hey everybody, welcome back to another video. In this video, we're going to talk about the cardiac output and the regulation of the cardiac output. It's going to be a cool one and a very interesting one. Let's get started. If you guys like the video, if it truly helps you, please consider subscribing, liking the video, maybe leaving a comment. It really does help push the video and help support the channel, and I really would appreciate it. So let's get started. Some of the topics we're going to talk about today is what is cardiac output, what is the equation for it, what is the heart rate, and where does it come from, and how do you calculate the average heart rate? What is the stroke volume? Where does it come from? What's the average number? What does a cardiac output have to do with exercise? Can your heart rate be regulated? How and can the stroke volume be regulated? And if so, how? What is the Frank-Starling law? How does it relate to length-tension relationships? And can the sympathetic nervous system affect the stroke volume? And a little more about venous return. Okay, so let's get started. So when we talk about cardiac output, here is that equation that we set. Cardiac output, or Q, equals to heart rate times the stroke volume. But what is the cardiac output? The cardiac output is actually defined as the amount of blood that you push out of your heart per minute. Okay? Now, how do you get that number? Okay, well, the actual units are in milliliters per minute, or, liters per minute. Okay, and you get that by taking your heart rate, which is in beats per minute, and multiplying it by your stroke volume, which was in liters or milliliters. Okay, and when you multiply these two, you become milliliters per minute. Okay, because it's beats per minute. Now, people get cardiac output sometimes confused with stroke volume. But remember, stroke volume is the amount of blood that you pushed out of your heart in one cardiac cycle. Okay? But if you want to figure out the amount of blood that you're pushing out per minute, you got to multiply the amount of blood you pushed out of the heart in one cardiac cycle by the heart rate. Okay? And then you can only get the cardiac output. Right? So now that we know what the cardiac output is, and now that we know it's being affected by the heart rate and the stroke volume based on this equation, let's go ahead and break each of these down, okay? So I'll write this milliliters here, and I'll write beats per minute here, and then I'll put above here that this guy is in milliliters per minute, or if you want, it's in liters per minute, okay? This guy can also be in liters. So now let's go ahead and talk about every single one of these. So how is heart rate generated? Where is that coming from? Well, heart rate, if you guys remember, is coming from the intrinsic autorhythmic cells of the heart, okay? Remember the SA node, the AV node, the Purkinjes, those guys, they have autorhythmic function. We mentioned this in the previous videos, okay? And they're able to generate the rhythm of the heart. They're able to set the heart rate. Now, who is the primary autorhythmic cell? It is the SA node. So the intrinsic cardiac conduction pathway goes like this, right? The SA node, then we move on to the AV node. After the AV node, we move on to the bundle of His, okay? The bundle of His. And then we move into the left and right bundle branches, okay? Which, by the way, if you're curious, here's the SA node, the AV node, right? SA node sends signals to the AV node, but at the same time, it's actually depolarizing the atria, allowing the atria to contract. The AV node holds onto the signal for about 0.1 seconds, sends it down to the bundle of His, which is here. Bundle of His carries that down to the left and right bundle branches. After the left and right bundle branches, we split into these little terminal endings called Purkinje fibers, okay? Purkinje fibers, which allow for very, very fast and rapid depolarization of the atria from the bottom, sorry, not the atria, the ventricles from the bottom upwards, okay? If you're curious about this pathway, we talked about this in more detail in a previous video. Go and check out the human physiology playlist. I'll link it here. Now, this is how the heart rate is generated, okay? It's being set by the SA node. And what is the approximate action potential rate of the SA node? Guys, it's about 100 beats per minute, okay? 100 action potentials. Now, if that is the case, why is your heart at rest not going to be at 100 beats per minute? Again, we talked about this in that same video that I mentioned, but essentially it is because your heart rate is being actively suppressed by what? Well, remember at the start of the video, I said that can the heart rate be regulated? And the answer is absolutely yes. It can be regulated by the autonomic nervous system, okay? So the sympathetic and the parasympathetic nervous system. And we know that at resting conditions, your heart is actively being suppressed by the parasympathetic nervous system. That's why your average heart rate is actually lower than 100. Now, this brings me to another point. How do I calculate my average heart rate? How do I do that? Well, if you guys remember from the cardiac cycle video, okay, we know that one cardiac cycle takes about 0.8 seconds, right? And in one cardiac cycle, the heart beats one time, okay? So if we want to figure out the average heart rate, right, that is actually measured in beats per minute, we can use our knowledge of the cardiac cycle. So we can say that if one beat of the cardiac cycle, right, if the heart beats one time and that occurs in 0.8 seconds, okay, we want to know how many times it beats in minutes. You do X number of beats over 1 minute or 60 seconds. And now you just cross multiply, and the answer that you're going to get is going to be 75 beats per minute, okay? So you see how we just mathematically just calculated our average heart rate just by knowing the cardiac cycle time, okay? Pretty basic concepts of physiology applied here. Now we know what our average heart rate is. It's about 75 beats per minute. Okay, not too bad. Not too bad. So now we know where the heart rate is coming from, and now we actually have the number for it. Now let's look at the stroke volume. Where is it coming from, and how do we get the number for that? So if you guys remember in the cardiac cycle video, guys, I mentioned this. I've mentioned this a couple times. But in the isovolumetric systole and the isovolumetric diastole phases, we get values that are going to determine our stroke volume. Because you know all your stroke volume is just going to be involving something known as the EDV and the ESV. Again, if you're interested in more detail, go and watch that video. But in the isovolumetric systole, okay, we essentially have a volume of blood that is remaining from the preceding diastolic phase. And that volume of blood that is inside of this actual ventricle at this current moment in time is called the end diastolic volume. And in that video, we said that it was going to be around 135 milliliters. Now, after this phase, we go through ventricular systole, and then we move on to isovolumetric diastole. If you remember, we said in the isovolumetric diastole phase, we have the volume of blood that is remaining after ventricular ejection. And that volume of blood, right, which was after the systole, was called the end systolic volume, okay? The volume of blood at the end of systole. And that guy was about 65 milliliters at rest, okay? Together, both of these guys will give us the stroke volume. You might be thinking, how so? Again, I discussed it in the cardiac cycle video, but the stroke volume essentially is just your end diastolic volume subtracted by your end systolic volume, okay? Remember, end diastolic volume comes first, okay? If you subtract this from this, you'll get the stroke volume, okay? Now that we have these average numbers, we can actually figure out the average stroke volume. So let's go ahead and do that, guys. We have 135 milliliters equaling to, subtracted by 65 milliliters. And guess what I get? I get about 70 mLs. Okay, that's beautiful, guys. We can actually say that if I take these two together, okay, if I take the 75 beats per minute and the 70 mLs, I can now calculate my cardiac output. Because now, look, I have the heart rate, I have the stroke volume, and now I can calculate my cardiac output at rest. Okay, and let's do that right here. So we have 75 beats per minute multiplied by 70 milliliters. And what do I get, guys? I get approximately 5,200 milliliters. Approximately, okay? I know that's not the number, but bear with me. I get approximately 5,200 milliliters. Um, but is that where I leave it at? No, it's milliliters per minute, okay? Because it's the amount of blood I'm pushing out of the heart per minute, and technically this is at rest. Now, an interesting fact that I have to bring up is that the cardiac output can increase during exercise, and that's due to many factors that we'll talk about. It's due to the heart rate increasing, it's due to the stroke volume increasing, and the stroke volume can increase due to an increased end diastolic volume and a decreased end systolic volume, which can be caused by a higher contractility of the heart, and this one can be caused by a higher venous return to the heart. We'll talk about all these factors, but essentially all of those will work to increase the cardiac output, okay? But how much can the cardiac output increase to? We said at rest it's about 5,200. Well, guess what? The cardiac output in individuals like me and you guys watching can go up to around 20 liters, maybe to 20 to 25 liters per minute, okay? At heavy aerobic exercise. In extremely conditioned cyclists and sprinters, numbers up to 40 liters per minute have been seen, but just for the safe range, we'll go around 30 to 35 liters per minute have been seen in athletes. But I've even read certain literature discussing 40 liters per minute. So you can see how the cardiovascular system is very dynamic in its nature to adapt and increase the cardiac output to meet the demands of the body. And another thing I'll tell you is that the cardiac output can be thought of as an index for the metabolic demand of the body, okay? So when you're at rest, the body's metabolic demand, for example, for oxygen or CO2 removal is pretty low, and thus the cardiac output remains low. But if the metabolic demand goes up, for example, you need more oxygen during exercise, guess what? The cardiac output has to go up, okay? And if the cardiac output is going up, guys, the speed at which that blood is reaching my tissues is going to be faster, okay? And thus, I'm meeting the metabolic demands of the body. So this is kind of a good way of looking at the cardiac output. Now, let's talk about what are the factors that are regulating the heart rate to change the cardiac output and how that's going to affect the cardiac output. So if you guys remember from the heart function and essay note structure video, we talked about these graphs and we had every single one of these scenarios laid out. But now we're going to actually look at how and where in this cellular pathway sympathetic and parasympathetic nerves are going to affect the SA node. So here's this diagram. Here's the central nervous system with the parasympathetic and the sympathetic nerves coming out and affecting this actual SA node, and we're going to zoom in on the interaction here at the cellular level, okay? So here is an SA nodal cell, just as a brief overview for you guys. We started out right over here in this pacemaker potential or slow diastolic depolarization, and we went from somewhere around -60 to about -55, and then all the way up to -40, which was our threshold potential. How did we do that? Well, here's the numbering. Number 1, the permeability of potassium decreased in the cell, and that opens up the funny type or F-type sodium channels to bring in sodium. Afterwards, these channels will close, but the positive charges that they brought in depolarize the cell to a voltage that will open up the T-type calcium channels. Once the T-type calcium channels open, they will bring in enough positive charges, these calciums, to depolarize the cell to the threshold potential. At that point, these channels close, and they open up the L-type calcium channels that are part of the action potential to reach that peak potential right over here, okay? At that point, at that peak potential, the L-type calcium channels close, and the potassium voltage-gated channels that were open at the start of this entire cycle open up again, and they'll repolarize the cell back down to -60. Okay, if you need a bigger refresher, go back and watch a video in this playlist. Now, at which points of this cycle, the cellular pathway, is the sympathetic and the parasympathetic going to be acting, and how would that increase or decrease or regulate the heart rates? Okay, so that's a great question. So first things first, I have to get something straight with everybody, okay? This graph, all it is doing is just reading the cellular events that are occurring in the cell. Okay, so any change in positive or membrane potential or ion movement, this graph is going to be picking up, right? Because it has millivolts on the y-axis and it's got time on the x-axis. Okay, so it's going to pick up the change in voltage inside of a cell over time. Now, with that said, let's look at the SA node's action when the sympathetic nervous system is acting on it. Now, when the sympathetic nervous system is acting on it, remember your sympathetic nervous system is your fight or flight. So if you see a bear, what's going to happen? You're going to get very scared, okay? Your muscles are going to get activated. They're going to start begging for a lot of oxygen, which means what? Which means you need to start bringing a lot of oxygen to them. But how are you going to do that? Well, you're going to have to increase your cardiac output. Well, how would you do that? One of the ways is by increasing your heart rate. How would you increase your heart rate? You would activate your sympathetic nervous system. The sympathetic nervous system, it is going to increase your heart rate by two main ways. You can see that it's changing the slope of this pacemaker potential, making it more steep, okay? And by making it more steep, look at what it's doing. It's helping us reach the threshold potential faster. And if I reach the threshold potential faster, guys, I launch the action potential faster. Then I repolarize faster, and then I reach it again faster. Okay? And this cycle will keep repeating, and now you can see that this original brown was the original SA node, and in blue we have the sympathetic nervous system being acting on the SA node, and you can see it's so much faster, and we also have more frequency of action potentials as well. Now, the frequency of action potentials means that, the higher frequency of action potentials means that we actually have a higher heart rate now. Okay, so this is indicating a higher heart rate. But how is it changing the slope of this graph? And remember, the only thing that is changing, okay, is the slow diastolic depolarization. You can see that the peak of depolarization in the action potential is not changing. The only thing that ever changes with sympathetic or parasympathetic stimulation will ever and always be the pacemaker potential, guys, okay? We're not changing anything else in this SA nodal autorhythmic cell. Now, with that said, where is it acting? Well, guess what? We want to bring in positive charges to reach the threshold potential earlier, right? That's the entire goal here. So what do you think it's going to do? Well, it's going to act on two places to do that. It will act on these funny sodium channels, okay, and upregulate their activity, bringing in more positive charges. If they bring in more positive charges, they're going to activate these T-type calcium channels sooner. And if they do that, the T-type calcium channels bring in calcium sooner than they were supposed to and help us reach threshold. But they don't just only act on the F-type sodium. They also upregulate the T-type calcium channels as well, upregulate their activity, okay? So now we got double the function here, okay? And we're bringing in a whole bunch of these guys to reach the threshold faster. All right? Awesome, guys. But the rest of it is the exact same, and that's because we're not acting on the action potential with the sympathetic nervous system. We're only acting on these guys, okay? And these guys are part of the pacemaker potential, not the action potential. The L-type calcium channel is part of the action potential portion, which is right here, and the pacemaker potential is right there. Crucial to understand the difference there. What about the parasympathetic nervous system? What is it doing? Well, the parasympathetic nervous system, guys, that is your rest and digest, okay? That means that you're pretty chill, okay? You don't need your heart rate to be high. And remember that the previous slide, we said that the reason why your heart rate is not at 100 beats per minute is because it's actively being suppressed. So we know that the SA node on the parasympathetic nervous system is going to be suppressed. How? Well, let's take a look at this actual graph. What do you notice first? There's essentially a hyperpolarization, okay? And for those of you who need a reminder, a hyperpolarization is is when I'm making the cell more negative than the resting membrane potential. And there's an initial hyperpolarization that you're going to notice here. And after that dip down, what you'll notice is that the slow depolarization is slower than usual, okay? It's actually taking us a very, very long time to reach the threshold potential, whereas over here, it would take maybe like 0.1 seconds. Over here, it's taking us like 0.8 seconds, okay? Those are just hypothetical numbers that I made up here, but you get the point. it takes us a much longer time to get to the threshold potential and cause an action potential, okay? Now, the fact that I changed the slope of this line to make it so not steep like this makes it so that I reach this actual threshold potential at a later time, and I launch fewer action potentials, thus reducing my heart rate, okay? And you can see that I've already drawn it out here, but the only place that this actual guy is going to act on, okay? Well, sorry, not the only place. It's going to act on two places, two or three places. One of them, the parasympathetic nervous system, is going to be this potassium channel. So not only is it going to upregulate the activity of this potassium voltage-gated channel to what? To cause that initial hyperpolarization phase, right? Because remember, potassium is a positive charge, and once its channel opens up, it'll immediately start going outside of the cell, making the cell negative, right? Why does it go out the cell? Because it's following its concentration gradient, okay? Again, if you need a refresher, go back and watch the previous SA node video. Now, that's why it's doing that. What else is this guy going to act on? Well, you know, the sympathetic nervous system was upregulating these guys. Guess what the parasympathetic nervous system is going to do? It is going to come here and downregulate the activity of both of these guys. Okay, it'll come and downregulate the activity of both of these guys. Isn't that fascinating? So not only are we actually bringing out more positive charges to make the cell more negative, but we're also bringing in less positive charges, which delays the cell becoming depolarized for a longer period of time, okay? So that's how the SA node, the parasympathetic nervous system is actually delaying SA nodal function, okay? And this is how you actually regulate heart rate. So to just briefly summarize it, you have the parasympathetic nervous system, okay? And you also have something else, guys. What do you have? You have the sympathetic nervous system. And they're both going to act on your heart rate. And you can see that the sympathetic nervous system will work to increase the heart rate, whereas the parasympathetic nervous system will work to decrease the heart rate. Awesome. And again, how does this all relate to cardiac output? Well, you have heart rate times stroke volume equals to Q, sometimes also written as cardiac output, like this, CO. But if I upregulate my heart rate, okay, and let's do it like this, let's color code. If I upregulate my heart rate, my cardiac output's going to go up, okay, it's a direct relationship, assuming my stroke volume is the same. If I decrease my heart rate, then my cardiac output will go down, okay? That's that little tidbit right there, guys. All right, now a small little note to make is that technically, the parasympathetic and the sympathetic nervous system, they also do give fibers to the AV node as well as the SA node, okay? And again, if you really do want to be particular here, the parasympathetic also kind of has fibers that go to the atrial muscle, but not the ventricular muscle, okay? But that's too advanced for this video, and perhaps we'll talk about it in another video, okay? All right. Now let's take a look at how do we regulate the stroke volume to change cardiac output, okay? So we learned about how do we regulate heart rate. Now we got to learn about how we can regulate the stroke volume. And this one's going to be a little bit more challenging, but I'm sure it's nothing you guys can't handle, all right? If you've made it so far to the video. So in this portion of the video, we're going to, split it into two scenarios. We're going to have one scenario, okay, where I have, and let me copy this color here. We're going to have one scenario where I actually have a high sympathetic nervous system activity. Okay, so I have a high sympathetic activity. And then I'm going to have another scenario where I have an increased venous return to the heart. What does it mean when I have an increased venous return to the heart, guys? Well, venous return, all it's talking about is veins that are coming into the heart, dumping their blood back to the heart, right? Their activity increases. What does that mean by their activity? Well, they're going to bring more blood back to the heart. When we say venous return is high, that means that more blood is coming back to the heart than it was at, let's say, resting conditions. But let's take a look at these hearts that I have drawn here, okay? And both of them. Let's take a look at both of them. And let's plot some differences just to get oriented. So right here, I have a heart in diastole, and you can see that it's getting filled, which is what diastole is. And then we have a heart in systole, where it is contracting and pushing blood out into the aorta and the pulmonary trunk. Same thing down here. Diastole, getting filled, systole, pushing blood out. What do you notice, though? What do you notice here? There's a difference. In the diastolic phase, what do you notice? Which one do you think has the higher amount of blood in it? The venous return one or the sympathetic activity one? Okay, well, it clearly to me seems to be the high venous return. The high venous return fills the ventricle up to the brim, okay? And the sympathetic activity one, nothing really changes. The ventricle just fills the same. But what do you notice between the systole phase? Well, in the systole phase, sure, there is actually less blood remaining inside of the venous, the venous return heart right now. But the sympathetic activity heart, what do you notice about it? Does the ventricle size look a little smaller as compared to this guy? It does. It does look a bit smaller. And which one has more arrows around it? The arrows, remember, from the cardiac cycle video, they were representing contraction. And the size also depicts how strong the contraction was. So what you're noticing in the image difference here is that this ventricle seems to be more contracted than this one, okay? Which kind of should give you a hint about what the sympathetic activity is doing, right? So we're going to associate these two scenarios, okay, with these little curves, okay? And these curves, okay, they're going to have a very, very important significance for us, okay? Let's look at this bottom one first. So this curve is a Frank-Starling curve, okay? So Frank-Starling is a law made by this guy named Frank and Starling. Starling actually observed this in around the 1914, this effect that I'm about to tell you about. And it's pretty interesting. He basically observed a length and tension relationship. Now, I'm not going to go through the length tension relationship of a skeletal muscle with you guys. You guys should already kind of know that. That looks kind of something like this, where the tension is rising and then it reaches this portion that plateaus and then it goes back down, okay? And we said that this portion that is plateaued is the optimal length for the muscle, okay? This part would be too stretched. This part would be this part would be too short, too stretched. This part would be too shortened, okay? Something like that. Well, for the heart, it doesn't work like that, okay? The length tension relationship doesn't work like that. There is no descending portion. There is only an ascending portion and a little bit of a plateau portion. There is no descending portion. And this is important to realize, okay? So there's only an ascending portion, but not a descending portion. So what is this going to look like? What does this even mean? Well, we got to look at the end diastolic volume, which is being plotted out in the x-axis, okay? And the stroke volume, which is being plotted out for us inside of the y-axis, okay? And trust me, you'll understand this perfectly by the end of my explanation here, okay? So if you guys remember from the first few slides of this video, what was the normal end diastolic volume? The end diastolic volume, okay? So the volume of blood at the end of diastole. If you're saying 135, pat yourself on the back here. It is indeed around 135 milliliters. And if you remember, we said that 135 corresponded to about 70 milliliters of stroke volume, okay? If you haven't, or if you can't remember that, just, go back and rewatch that portion very quickly. But we said that occurs, okay? We said that occurs, and, let's fix this up a little here. There we go. Now, okay. So this right here is at resting scenarios, okay? 135 end diastolic volume correlates to 70 mLs. And you're probably thinking, how does this correspond to a length and tension relationship? Well, I'll get to that in a second, guys. Just give me a second. Now, With the venous return, you know what's going to happen? If I have high venous return to the heart, okay, a high venous return to the heart is going to fill this ventricle up to the brim, okay? You know what lines the walls of this ventricle, guys? The inner part? Your myocardium, the muscle, the myocytes, okay? And what do you think is going to happen to these myocardium or these myocytes if the ventricle is absolutely filled with blood? That blood will keep pushing on the walls of that actual ventricle, okay, and stretch out that ventricle, okay? Hopefully that's making sense right now. The blood that's coming in because of the increased venous return is going to fill up this ventricle and it's going to push on these walls of the ventricle, making it super stretch, making the myocytes super stretch. If the myocytes are stretching, okay, they are actually reaching a, a state of sarcomere length that is more optimal for contraction, okay? And that is the Frank-Starling law. So the Frank-Starling law, all it is saying, if I was to give you guys the skinny on it, Frank-Starling law says that if the myocytes are stretched more, okay, that is going to lead into a higher stroke volume, okay? So the higher the amount of stretch on the myocardium, the higher the stroke volume. And how do I prove this to you? Well, if I have a higher venous return, what's going to happen to my end diastolic volume, which is right here? What do you think is going to happen to my end diastolic volume if my venous return is high? Well, obviously it'll be high, right? Because remember, an end diastolic volume is just the amount of blood that is left inside of the ventricle at the end of diastole. And if I fill the ventricle up more in the diastolic phase due to a high venous return, then my EDV is going to be high. Okay? So instead of maybe starting at 135, this time around, maybe we'll start out here. Okay? Maybe we'll start out here. And because we started out here, maybe, guys, just maybe, we correlate to about, let's say, 100, okay, stroke volume. So we started out here, and we go up to a stroke volume of 100. So that's intriguing, okay? At a higher end diastolic volume, I ended up getting a higher stroke volume. Why? Well, it's because of the fact that a higher end diastolic volume stretches the walls of the myocytes to increase stroke volume. But there's actually, there's actually more to this. This is just a simplified version of what the Frank-Starling law is saying. What does it actually mean? Well, take a look. This portion to this portion, okay? Let's say that's the length of this actual myofibrils, okay, or the sarcomere during diastole, okay? Let's say that's the length of the myofibrils during diastole in this portion of the curve. But the more I approach this portion of the curve, they start to become more and more like this, okay? When the myocytes become stretched, what ends up happening is that the thick and the thin filaments, remember the actin thin filaments and the myosin thick filaments, they start to overlap more as the heart is getting stretched and more by the end diastolic volume and then going into systole. That is placing the actual myocytes in a more optimal length or optimal position to contract, okay? So we can say that, at this position, this is what the myocytes would look like, and at this position, this is what they will look like. Incidentally, what is this part of the graph called? Well, this part of the graph is I naught, and it actually just stands for the optimal length, okay? And in physiological conditions, you cannot stretch the myocardium past this point, okay? You cannot stretch it past this point, and this is why I say that there is no descending limb of this actual graph. There is only an ascending limb. So, just to recap with you guys, the Frank-Starling law states that if I increase the stretch on my myocytes, okay, I am going to increase the stroke volume. But how am I actually doing that? Well, one way is if I increase the venous return back to the heart during the diastolic phase, I'm going to increase the end diastolic volume. And that end diastolic volume is going to push on the walls of this actual, the high EDV will push on the walls of this actual ventricle, stretching the myocytes. If I stretch the myocytes, guys, that is going to help them reach an optimal length. Okay, this optimal length where the myosin and the actin can interact more properly. If they imagine at this phase over here, okay, we are more to the left, we're more towards this configuration. Whereas over here, we're more towards the right and closer to this configuration, closer to the optimal length. Okay, the closer I am to the optimal length, the better the myocytes are able to interact with one another. Not the myocytes, the actin and myosin are able to interact with one another. The further away I am from the optimal length, the less optimally they're going to interact with one another. Okay? So let's do a quick summary of this. A high venous return, okay, can increase the end diastolic volume, which will then increase the stretch on the myocyte, okay? And the myocyte getting stretched will reach an optimal length, okay? And what ends up happening is when they reach an optimal length, like I said, the myosin and the actin can interact more accordingly and optimally, and this can increase something called contractility, okay? Contractility is just the ability of the heart to contract. So, and when I say we enhance contractility, that means there's better contraction occurring, okay? More forceful contraction. So we have an increase in contractility because more myosin and actin heads are interacting. And what do you think is going to happen, guys, if I forcefully contract? If I contract more forcefully than I would normally, what do you think is going to happen to the volume of blood at the end of systole, the ESV, essentially? Would it be higher or lower? And if you're saying lower, pat yourself on the back here, okay? If I contract more forcefully from my ventricle, I push more blood out of my ventricle, okay? And, we said that because, this high EDV constituted a high stroke volume. But really, the story was going like this, okay? Increase EDV, increase stretch of the myocyte, reaching optimal length, which increases the contractility, which eventually decreases your ESV. And look, we end up finally increasing the stroke volume, okay? Just a side note, anything that wants to increase or modulate the stroke volume has to end up acting by modulating the end diastolic volume and the end systolic volume. And that is due to the nature of the equation here, okay? Anything that has to modulate this has to modulate these two, or one of these two at least, okay? All right, guys, so that is the scenario with the venous return, okay? And by the way, this blue curve right here. This is a normal Frank-Starling curve, okay? It's just that over here we are at rest where there is no venous return, but over here there was venous return, okay? Now, and we also talked about the length and tension relationship here, okay? So this is the optimal length, which leads to the highest tension produced. Tension just means force, okay? And in this case, you can think of stroke volume as the amount of force here, okay? Now, this first scenario, which is a little bit harder, that's why I left it for last, is this high sympathetic activity. Guys, if my sympathetic activity goes up, okay, a couple of things are going to happen. And I told you that one of the main differences that you can see between this heart and this heart is that this one is a bit more contracted, okay? It's a bit more contracted and it's generating more pressure. And why is that? So in this scenario, we have a high sympathetic activity, but remember there is no venous return, okay? So VR is just venous return. There's no venous return here, okay? I'll show you an example with venous return as well, but for now, just let's focus, there's no venous return. If there's no venous return, let's take this right here. Again, an end diastolic volume of 135, okay? And we know that that correlates to about a what, guys? To about a 70 milliliter stroke volume in a normal person. But now let's say there's going to be sympathetic stimulation of the heart. Which part of the heart? The SA node? No, not really, because we said regulating the stroke volume, not the heart rate. And the stroke volume refers to the amount of blood ejected within one cardiac cycle. And who's responsible for the ejection of the blood? The ventricular myocytes. So that means the sympathetic activity, or the sympathetic nervous system, is acting on the ventricular myocytes. And we'll look at that pathway in a second. But for now, bear with me. The sympathetic nervous system, Frank-Starling curve. So we have a Frank-Starling curve for a normal heart with no sympathetic activity, okay, so no SNS. And we have a Frank-Starling curve of the normal heart with sympathetic activity, okay? And that sympathetic activity specifically is occurring on the ventricular myocytes. What is that going to look like? You can see that without changing the venous return, okay, without changing the end diastolic volume, in other words, okay, if I remain at that same end diastolic volume, I actually increase the the stroke volume of my heart. Okay, take a look at it. So right here, without even changing my end diastolic volume, because I didn't change any venous return, I was able to increase the amount of blood I pushed out of my heart. Awesome. How did I do that? How does this sympathetic activity do that? Well, let's go ahead and take a look, guys. Let's go ahead and take a look. So here is going to be the mechanism of how the sympathetic nervous system activity is able to increase ventricular myocyte contraction. And if you're talking about bringing in calcium, then you're on the right tracks in your brain right now, okay? You're very, very, very close to the right tracks. So let's take a sympathetic neuron here, okay? Let's say this is a sympathetic neuron right here, sympathetic nervous system. We know that from the sympathetic nervous system, we're secreting these chemicals like norepinephrine and epinephrine. Okay, we're just going to represent it as a circle here, okay? And that norepinephrine and epinephrine, they will bind to a specific receptor on the surface of this ventricular muscle cell, okay? You've seen this kind of diagram in my previous video on the ventricular contraction. But there's a specific kind of receptor here, okay? If any of you have taken any molecular biology class or endocrinology class or a cell biology class, you will have heard of these. These are called a metabotropic receptor, but specifically, this one is called a beta-1 adrenergic receptor. Why is it adrenergic? Because it's responding to adrenaline, norepinephrine, and epinephrine. So beta-adrenergic receptor, but specifically beta-1. Why beta-1? This is just the isoform or the type of this receptor that's found in the heart. There are more than, there's beta-1, beta-2, beta-3. Don't worry about it, okay? Just know that beta-1 found in the ventricular muscle of the heart, okay? And when the norepinephrine and epinephrine, either or, not both, bind to this beta-1 adrenergic receptor, they're going to activate something that is bound to the intracellular side of this actual beta-1 receptor. This beta-1 receptor, by the way, you can sometimes call it a G protein coupled receptor, and you'll see why in just a second. The intracellular domain or side of this actual receptor is bound to something called a G protein, specifically a G stimulatory protein. And this G stimulatory protein, as soon as the norepinephrine and epinephrine bind, it will get activated, okay? Once this G stimulatory protein is activated, it'll go and activate an enzyme, a very specific and special enzyme, on this actual cell membrane. This enzyme is called adenylate cyclase. This is what AC stands for. Adenylate, okay, cyclase or cyclase. And what this guy is going to do is he's going to take a molecule that you guys know called AMP, so adenosine monophosphate, and it's going to cyclize it and turn it into cyclic AMP. This cyclic AMP is a very cool molecule. It's a secondary messenger, okay? It will go and bind to a specific enzyme that is, free floating here. and activate that enzyme, okay? What is that enzyme called? This enzyme is a kinase. If you guys have taken biochemistry, you'll know that any enzyme ends with ase, okay? It ends with the this little ase phrase here, okay? And a kinase is an enzyme that is able to put on a phosphate group on proteins, okay, and other things. So a protein kinase A is just a kind of enzyme that is able to put phosphates on things. What kind of things? Well, this cyclic AMP will activate this protein kinase A, and this protein kinase A will come over here, and it'll activate this specific channel on the T-tubule of this membrane. You guys know this channel. It's called an L-type calcium channel. It'll put phosphates on top of it, okay? And what ends up happening is this will open up this channel. Okay, so look, here was the gate closed. Now the gate opens up in response to protein kinase A putting phosphates on this guy. What is that going to do? It's going to bring the calcium that was outside inside. And you guys know that when calcium comes in the cell, it can either go and bind to troponin, or the majority of it in this scenario is going to cause calcium-induced calcium release from this ryanodine receptor that is on the surface of the sarcoplasmic reticulum. If it does that, guys, okay, if it causes calcium-induced calcium release, the calcium from the SR will now come outside, and it'll come and bind to the contractile machinery, specifically the troponin. Once it does that, okay, we are actually going to go from a relaxed state to a contracted state. Why do we do that? Because calcium binds to troponin, okay, which moves this orange tropomyosin aside, allowing for these myosin and actin heads to interact with one another and go through cross-bridge cycling in sliding filament theory, okay, aka just increasing contractility of the heart at a given end diastolic volume. Another cool thing that this protein kinase A will do is not only will it speed up the rate at which a contraction is occurring, but it can also come here and act on the circa, okay, and put phosphates on it and increase the rate of calcium removal, which is facilitating the relaxation of the heart. So here I can put the calcium getting taken up again by the circa, okay? What does this kind of look like graphically? Okay, if you guys remember from my ventricular action potential video, okay, I showed you a graph that had the ventricular action potential, and I showed you another graph that had a ventricular contractile response, okay? Now, let's say that in red is going to be the ventricular contractile response right here, okay? That's going to be what it was at rest, no sympathetic stimulation, okay? Let's say normal force production, okay? Normal heart force, ventricular force. But when it comes to that sympathetic stimulation, here's what's going to happen to it instead, okay? So what do you notice happened here? What do you notice happened here, guys? Not only did the peak of force production change, so not only did I produce more force here, okay, and let's write that down. So here's the SNS force, sympathetic nervous system force, with the heart, okay, and again, this is the heart. Not only did the peak of force generation went up, but the rate at which I reach the peak increases, and the rate at which I relax increases as well, okay, or decreases, okay? So I'm doing all of this faster, and so what that's doing is it's shifting the curve to the left, and it's shifting the peak up, okay? So that's very interesting, okay? And some of you might be asking, okay, well, Kian, how do you know this is shorter than the other? Well, I didn't draw it, but this would technically be a graph over time, okay? And so if we were to time it, this guy would be here and take, let's say, 4 milliseconds, and this guy would already have gone through like half of its contraction in like 1 millisecond, okay? It's whatever, okay? You guys get the point. But This is what's happening with the sympathetic nervous system stimulation, okay? Here was the molecular mechanism of how it's acting to increase the contractility and increase relaxation as well, okay? All of this to say what? All of this to say that the sympathetic nervous system has the ability to increase the contractility of the heart, okay, and increase the stroke volume at the exact same end diastolic volume as before. But we also know that an increase in venous return can increase contractility, not by any of this pathway, by just causing the Frank-Starling law to occur, increasing the stretch of the myocytes, which will eventually increase the stroke volume, okay? So we can also say in this scenario, right, that because we increase the contractility of the heart, what would happen to our end systolic volume? It would go down here as well, okay? Now, something I have to mention to you about sympathetic nervous system activity is that when these experiments were done, okay, they were done in isolation, okay? So they only measured sympathetic activity on the ventricle's ability to increase its contractility, and then they only measured venous return back to the heart. But something you do have to know, and that we'll talk about, is that when the sympathetic nervous system gets activated, it can also, on top of, acting on the ventricular myocytes to increase their contractility through this pathway, it can also increase venous return. Okay, it can also increase venous return, and we'll talk about that a little next slide when we put everything together. And if that is the case, you're going to get a double response. And so we're going to look at that over here in a little summary, okay? So we can say that, for example, a normal curve, all right, a normal Frank-Starling curve with an end diastolic volume of 135 minus an end systolic volume of 65, okay, these are the average values, will grant us a stroke volume of 70. Okay, we all know this. And we looked at a curve or an example with the sympathetic nervous system being at play there. If the sympathetic nervous system is only acting without any venous return, okay, you will have, for example, an end diastolic volume, still 135, right, because no changes in venous return, but your end systolic volume would go down, and let's say it goes down to about 35. In that scenario, you would have a stroke volume of about 100 milliliters. Okay, so you can see how the stroke volume still went up without any change in the venous return by modulating just this variable. Okay, but what if we modulate both variables now? And how would you do that? I remember I told you that the sympathetic nervous system can also activate the venous return as well. And so this would be the greatest response here. Let's take a look at this response. Here you have, for example, an end diastolic volume of 175 due to the increased venous return, and you have an end systolic volume of, let's say, 35 because you increase contractility. And what you're going to end up with, guys, is a stroke volume as 140 milliliters, okay? The highest one. The highest comes when you put the increased venous return and the increased sympathetic activity together, all right? Now, that's going to finish it for regulating the stroke volume, okay? One more thing I have to tell you is that, and we'll talk about this more when we talk about the circulatory system, but the extent to which I fill the heart, okay? The extent to which I actually fill the heart in the diastolic phase is called preload, okay? It's called preload, and that is the extent to which I fill the heart. So, as an example, if I increase my venous return, I am increasing my preload, or the extent to which I'm filling the heart, which will then increase my end diastolic volume, okay? And that will increase my stroke volume. You will see later on, again, when we'll talk about the vasculature or the circulatory system, that three things determine stroke volume, and they're going to be preload, which is related to the end diastolic volume, and another one that is afterload, okay? And then another one that's contractility. And we've touched on two of those in this video. We've touched on preload, and we've touched on contractility, which can arise from sympathetic activity, okay? Yeah. Anyways, that's all I wanted to mention with that one. Now, Um, Again, here's our favorite formula: heart rate times stroke volume equals the cardiac output. We know that if I increase my stroke volume, my cardiac output would increase, and if I decrease it, cardiac output would decrease. How does this look like on a final summary slide? Okay, so in a final summary slide, we know that a couple of things are helping modulate activity. With the sympathetic nervous system, guys, the sympathetic nervous system, if it goes up, what happens to my heart rate? My heart rate goes up, okay? What happens if my parasympathetic nervous system activity goes up? Well, if this goes up, the heart rate goes down, okay? All right. What about the stroke volume side? Okay, the sympathetic nervous system can intrinsically or directly, not intrinsically, it can directly, I'm going to write this down, directly act on the stroke volume, or it can also indirectly act on it by modulating the venous return. But directly, it can act on the stroke volume and increase it, okay, which will then increase your cardiac output. Okay, there should be an arrow here. Should be an arrow here. And what do you notice? What do you notice? You'll notice that I've increased the heart rate here once, and I've increased the stroke volume here once, just by activating my sympathetic nervous system. And so right now, I've double increased it. But you know, that's not all. The sympathetic nervous system, when it gets activated, it'll also indirectly increase cause an indirect increase in stroke volume by increasing the venous return, which will then increase the preload, which will then increase the end-diastolic volume, which will increase this, which will triple increase this, okay? And another thing you will notice is that lowering the heart rate, okay, can actually get a down arrow there because of the increased parasympathetic nervous system activity, okay? So this is the kind of integration slide right there for the summary. But guys, we covered a lot today on regulating the heart rate, the stroke volume, and on top of everything, regulating the cardiac output, what it is, and we checked off everything that we wanted to talk about here, okay? If you really enjoy the video, if you truly enjoyed it, and it taught you something, please consider leaving a comment, subscribe, like, and share the video to others that you might find would enjoy it. Thank you very much, and I'll see you in the next video.